Hi, I'm Renshi. I'll kick off our presentation on bridging Gaussian and mesh for 4D closed human reconstruction from a monocular video developed together with Yu Yunshuan and Wu Jiacheng. Why does 4D human reconstruction matter? Traditional methods are slow and expensive. Deep learning offers fast, low-cost, and scalable alternatives crucial for applications like virtual try-ons, avatars, and animation, but it's still challenging because closes are highly deformable and hard to track. Temporal consistency is critical, but motion blurs and occultations, especially with only one camera, make it difficult. Single view input increases ambiguity and reduces accuracy. To address this, we combine 3D splatting with mesh topology, leveraging both flexibility and structure. And we introduce motion bases to model closed deformation efficiently over time, and use differentiable rendering for strong 2D supervision, ensuring accurate alignment.
Before we start the method part, we first learn a differentiable rendering method, 3D Gaussian splitting. As shown in this demo, it uses a set of elliptical bars named 3D Gaussians, each with its own position, size, color, and opacity. When a view is selected, these Gaussians are projected onto the 2D plane to form a rendered image. Since the representation is explicit and differentiable, it is suitable to train the model. For our 4D closed human reconstruction, we divide the pipeline into two branches, body and garment reconstructions. Given an input video, we first estimate human body motions. Inspired by the driven relationship between body and garment, we extract body part motions, which serve as the motion basis for garment deformation. In the garment reconstruction branch, we reconstruct first frame garment mesh as the template. Then we attach each Gaussian to the barycenter of each mesh face, which checks the complementary advance of fast rendering and garment topology. Then, all garment meshes are generated by deforming from the first frame. Based on the motion basis, each garment only needs to lend a coefficient vector at each time step. Then its deformation is calculated as a weighted combination of these bases. To align the 3D mesh with 2D observations, we perform the differentiable rendering to obtain 2D render images, which are then supervised with rare 2D observations to optimize the 3D garment mesh. To preserve physical plausibility, we also incorporate physical losses and garment body collision loss. Finally, our method achieves accurate and temporally consistent garment reconstruction.
Okay, here are our results on the dress 4D datasets. The right shows the target video, and the left side shows our reconstructions. Our closing mesh closely follows the ground truth video across all frames, and it generally exhibits correct bending and deformation throughout the frames. As the character moves, the closing accurately reflects the bending and torsion corresponding to the human motion. You might also wondering about the differentiable rendering results. So here we show RGB depths and normal rendering, which align also closely with the target video, demonstrating our model's effectiveness. So thank you for your listening.